Hello everyone, my name is Sneha. I am a student of BSc Chemistry Honours 6th semester. Today I will make a video for visually impaired students on the topic fats, oils and detergents. Oils and fats are widely distributed in nature, both in animal and plant kingdoms. In animals, they are present under the skin and in muscles, but in plants, they are mainly found in the seeds. Some important examples of fats are butter, tallow, beef, etc. While groundnut oil, cottonseed oil, olive oil, palm oil, coconut oil, sunflower oil, soybean oil, linseed oil, sesame oil, etc. are important examples of vegetable oils. Fats and oils are one of the three major constituents of our food, the other two being carbohydrates and proteins. In fact, fats and oils serve as energy reservoirs for the animals. In human beings, only a few hundred grams of glycogen, carbohydrate, can be stored, which can barely supply the body's energy need for about 12 to 18 hours. In contrast, large amounts of fats, 12 kg for an average person weighing 70 kg, can be stored, which can supply the body's energy needs for about 8 weeks. Besides this, oils and fats serve as raw materials for a large number of industries such as soap, paints, varnishes, and vanaspati ghee, etc. Natural fats. The fats obtained from animal sources such as butter from milk of cows and buffaloes, lard from hogs, and tallow from sheep, goats, etc. are called natural fats. This name is simply given to differentiate these fats from those fats which are obtained by hydrogenation of oils. Edible and non-edible oils. Oils such as groundnut oil, sunflower oil, soybean oil, rapeseed oil, mustard oil, olive oil, sesame oil, which are used for cooking purposes, are called edible oils, while oils such as cottonseed oil, linseed oil, castor seed oil, and moa oil, which are used in soap, paints, varnishes, and lacquer industries, are called non-edible oils or industrial oils. On the basis of iodine values, oils have also been classified as drying, semi-drying, and non-drying oils. Industrial oils may include essential oils or mineral oils. Essential oils such as rose oil, jasmine oil, lavender oil, eucalyptus oil, peppermint oil, etc. are volatile oils isolated from plants. Essential oils may be hydrocarbons, alcohols, aldehydes, ketones, esters, but not esters of glycerol, etc. For example, peppermint oil, an essential oil, contains menthol, an alcohol, as its chief constituent. Essential oils are mainly used in perfumes, cosmetics, and in pharmaceutical products. On the other hand, mineral oils such as paraffin oil is a mixture of saturated and unsaturated hydrocarbons and not esters or glycerides. They cannot be saponified. They are called oils simply because of their physical appearance. They are non-edible and are mainly used as fuels. Triglycerides, composition of oils and fats. As stated above, fats and oils are triesters of glycerol with higher aliphatic monocarboxylic acids. In other words, they are triacyl glycerols and are commonly known as glycerides. Fats and oils may be represented by the formula fatty acids. With only a few exceptions, all the monocarboxylic acids isolated from fats and oils are straight chain compounds containing 3 to 18 carbon atoms. Further, with the exception of only C3 and C5 acids, all other acids found in fats and oils contain even number of carbon atoms. The chief saturated fatty acids present in oils and fats are, besides saturated fatty acids, unsaturated fatty acids containing one or more double bonds in cis orientation may also be present in oils and fats. The chief unsaturated fatty acids present in oils and fats are oleic acid, linoleic acid, C17H31COOH, classification of glycerides. The three fatty acids in glycerides may be same or different. Therefore, glycerides are classified as simple or mixed glycerides according as they have the same or different acid residues. Glycerides are further classified into saturated and unsaturated glycerides according as they contain saturated fatty acids residues or unsaturated fatty acid residues. Both simple and mixed glycerides are found in natural oils and fats. In fact, oils and fats are complex mixture of mixed glycerides along with small amounts of simple glycerides. Chemical difference between oil and fats. The main difference between oils and fats is the proportion of saturated and unsaturated glycerides. Triglycerides with higher proportions of saturated acid residues such as palmitic acid, stearic acid are solids at ordinary temperature 298 Kelvin and are called fats, while those with higher proportion of unsaturated acid residues such as oleic acid, linoleic acid, etc. are liquids at ordinary temperature and are called oils. Melting points of glycerides. As stated above, fatty acids have one or more double bonds having less stable cis stereochemistry. For example, oleic acid has one cis double bond at C9, linoleic acid has two double bonds at C9 and C12, while linoleic acid has three cis double bonds at C9, C12 and C15 positions. These cis double bonds have vital biological importance. In the solid state, the molecules of saturated fatty acids fit closely in the crystal lattice due to their zigzag tetrahedral structures. On the other hand, cis unsaturated fatty acids have a bend at the double bond and hence do not fit closely, thereby lowering their melting point. Fats, chemical properties. Fats and oils, being triesters of glycerol, show all the reactions of simple esters. In case of glycerides contain unsaturated fatty acid residues, they also show the usual addition and oxidation reactions of alkenes. Some important reactions of fats and oils are given below. Hydrolysis. Fats and oils are readily hydrolyzed by treatment with superheated steam, mineral acids or alkalis. Hydrolysis is by superheated steam or mineral acids gives a mixture of fatty acids and glycerol. However, when the hydrolysis is carried out by alkalis, glycerol and salts of fatty acids are formed. Since the salts of higher fatty acids thus formed are used as soaps, the alkaline hydrolysis is commonly called saponification. In the digestive system of human beings and animals, fats and oils are hydrolyzed, glycerol and fatty acids by a number of enzymes called lipases. Hydrogenation. Oils which contain a higher proportion of unsaturated glycerides add on hydrogen in the presence of finely divided nickel as catalyst to form solid fat. This process is called hydrogenation or hardening of oils. It is similar to catalytic hydrogenation of alkenes and involves the reduction of double bonds present in unsaturated glycerides to form saturated glycerides. This process is extensively used for the manufacture of vanaspati ghee such as dalda, rad, gagan, etc. from groundnut, peanut, sunflower and other edible oils. Hydrogenation is never carried out to completion but is stopped as soon as the fat of consistency comparable to ghee is obtained. The completely hydrogenated fats are too hard to be useful as kitchen shortenings. The main advantage of hydrogenation is that as compared to oils, fats, hydrogenated oils have better storage qualities and do not become rancid easily. Hydrogenolysis. Conversion to alcohols. Fats and oils on treatment with hydrogen at high temperature and pressure and in presence of copper chromide as catalyst undergo reductive cleavage to form glycerol and long chain aliphatic alcohols. The splitting of a fat or an oil to glycerol and a higher long chain alcohol by hydrogen is called hydrogenolysis. The long chain alcohols thus produced are used for the manufacture of synthetic detergents. Transesterification. Fats and oils can be converted into simple esters of carboxylic acids such as methyl ethyl esters etc. by trans-esterification. It involves the treatment of a fat or an oil with a large excess of a suitable alcohol in presence of acidic or basic catalyst. The process of trans-esterification is quite useful for the large-scale preparation of long-chain fatty acids and long-chain primary alcohols of high purity. For this purpose, the mixture of methyl esters obtained by trans-esterification is subjected to fractional distillation to separate the individual esters. These, upon hydrolysis, yield fatty acids of high purity. Alternatively, the individual methyl esters are reduced to get long-chain primary alcohols. Addition of halogens. Like alkenes, unsaturated glycerides and halogens across the double bond to form addition products. The addition of iodine is usually carried out by treating the fat or the oil with iodine in presence of mercury chloride as catalyst. Since the amount of iodine used is proportional to the number of double bonds present, therefore this reaction is used for determination of extent of unsaturation in a given fat or the oil. Rancidity. When fats and oils are exposed to warm air and moisture for a long time, they develop a disagreeable smell and taste. This process is called rancidity and involves the hydrolysis of esters to produce fatty acids and oxidation at double bonds to form short chain acids and aldehydes. These short chain acids and aldehydes are volatile and have offensive smells. Therefore, they impart unpleasant odors to oils and fats. Rancidity is of the following two types. Hydrolytic rancidity. This type of rancidity is caused by the liberation of lower fatty acids by hydrolysis of triglycerides. For example, when butter is exposed to warm air and moisture, the hydrolysis of the glycerides in butter yields butyric acid and other volatile acids, caproic, caprylic, capric acid, etc. with the unpleasant odors. This process of hydrolysis is catalyzed by enzymes, lipases, which are provided by the microorganisms present in air. This type of hydrolytic rancidity can, however, be checked by keeping the butter covered in a refrigerator. Oxidative rancidity. This type of rancidity is caused by oxidation of an unsaturated triglycerides by air to form short chain acids and aldehydes having unpleasant smell. It is believed that the first ester linkages are hydrolyzed to yield unsaturated acids which undergo oxidation at the site of double bonds to produce short chain acids and aldehydes. Oxidative rancidity can be prevented by the addition of certain chemicals, generally phenols, called antioxidants. Two antioxidants which occur in the natural fats are vitamin C and vitamin E. Analysis of fats and oils. Fats and oils are extensively used in a number of industries. Therefore, it is essential to check the quality of a given fat or an oil. This involves the determination of physical constants such as melting. Analysis of fats and oils. Fats and oils are extensively used in a number of industries. Therefore, it is essential to check the quality of a given fat or an oil. This involves the determination of a physical constants such as melting point, specific gravity, refractive index, etc. and chemical constants such as acid value, iodine value, saponification value, Richard-Missel value, etc. Some important chemical constants are described below. Acid value. It is defined as the number of milligrams of potassium hydroxide required to neutralize the free fatty acids present in 1 gram of a fat or an oil. The acid value is determined by dissolving a known weight of the given fat or the oil in pure neutral alcohol and titrating against standard KOH solution using phenolphthalein as an indicator. The acid value is a measure of free acids present in a given fat or oil. A high acid value indicates that the given sample of the fat or oil is quite old and has become rancid. Saponification value. It is defined as the number of milligrams of potassium hydroxide required to completely saponify 1 gram of the fat or oil. In other words, it represents the amount of potassium hydroxide in milligrams required to neutralize the fatty acids formed as a result of complete hydrolysis of 1 gram of the fat or oil. Saponification value is determined by refluxing a weight quantity 1 to 2 gram of the fat or oil with a known excess of standard alcoholic potassium hydroxide solution and then titrating the unreacted alkali against the standard acid. For example, saponification values of trilurid and tripalmitin can be determined as follows. Thus, the saponification value gives an idea about the molecular weight of the fat or the oil. Obviously, smaller the saponification value, higher is the molecular weight. For example, tripalmitin molecular weight is equals to 806, has a saponification value of 208, whereas trilurate with molecular weight 638 has a saponification value of 263. The saponification value also indicates the length of carbon chain of the acid moiety present in the oil or fat. The higher the saponification value, greater the percentage of short chain fatty acid in the glyceride of the fat or oil. Butter with short chain fatty acids has saponification values between 210 to 230, whereas soybean oil has saponification values between 189 to 195. Saponification value is used to determine the adulteration of a fat or an oil with some other oil or fat with lower or higher saponification value, or even by some saponifiable matter. Iodine value. It is defined as a number of grams of iodine that will combine with 100 gram of the fat or oil. Iodine value may be determined by any one of the following two methods. Hubble method. In this method, a solution of a known weight of the fat or oil in CCl4 is allowed to react with the known excess of a standard solution of iodine in ethanol in presence of mercuric chloride as catalyst. The unreacted iodine is then determined by titrating it against standard sodium thiosulfate solution using starch as indicator. For example, the iodine value of triolene may be calculated as follows. Witt's method. In this method, a solution of the more reactive iodine monochloride ICI in glacial acetic acid is used in place of iodine mercuric chloride. A known weight of the oil fat is dissolved in CHCl3. Witt's solution ICl in CHCOOH is then added. ICl adds across the double bond. ICl left unused is then treated with Ki solution to liberate an equivalent amount of iodine. The liberated iodine is then titrated against standard hypo solution using starch as indicator. The amount of ICl that has added across the double bond is then determined using the following relation. Iodine value is a measure of the extent of unsaturation present in an oil or fat. Higher the iodine value, more unsaturation is the oil or fat. Unsaturated is the oil or fat. For example, iodine value of linseed oil is 170 to 185 and tung oil 163 to 171, soybean oil 127 to 138, sunflower oil 140 to 156 and olive oil 80 to 100. Richard Missel value, that is RM value. It is defined as the number of milliliters of 0.1 normal KOH required to neutralize the steam volatile fatty acids obtained by complete hydrolysis of 5 gram of the fat or oil. To determine the RM value, a known weight of the fat or oil is completely saponified with alkali. The resulting solution is acidified with dilute H2SO4 and then subjected to steam distillation. The distillate, which contains the volatile acids, is then titrated against 0.1 normal KOH solution. RM value is a measure of the volatile fatty acids residues present in a given fat or oil. It is highly useful for testing the purity of a butter or desi ghee, which contain a relatively high proportion of glycerides or butyric and other steam volatile and residues. The RM value of adulterated butter is always lower than that of pure butter. Industrial oils of vegetable origin, drying oils. Certain oils such as linseed oil, tung oil, China wood oil, perilla oil, etc., when exposed to air in thin layers, form hard and tough water insoluble solids. This process is known as drying, and such oils are called drying oils. Oils like olive oil, groundnut oil, which do not dry on exposure to air, are called non-drying oils, and those which dry slowly, such as cotton seed oils, are called semi-drying oils. Chemically, drying oils contain a high percentage of unsaturated glycerides as shown by their high iodine values. On the other hand, non-drying oils have low iodine values while semi-drying oils have intermediate iodine values. For example, drying oils have iodine values above 150, linseed oil iodine value 170 to 185. Non-drying oils have iodine values less than 100, while semi-drying oils have intermediate iodine values. Unsaturated glycerides contain linoleic acid and linolenic acid as the unsaturated fatty acid residues. These acids contain 2 or 3 isolated double bonds respectively. In general, drying oils containing unsaturated glycerides with conjugated double bonds dry more rapidly than those containing isolated double bonds. Drying oils are used as a medium for paints, varnishes, lacquers. In fact, paints are suspensions of some pigments or the organic coloring matter in linseed oil, to which some turpentine oil has been added as a thinner. When these paints are applied on any wooden or iron surface in the thin layers, they quickly dry up to form a tough organic film which protects the surface being painted. Mechanism. The actual process of drying does not simply involve removal of moisture or evaporation of solvent but involves complex changes. It is believed that the reactive allylic hydrogens present on the carbon next to the double bond present in the unsaturated glycerides are first attacked by the oxygen to form hydroperoxy compounds, which then combine with the allylic hydrogen of the other glyceride molecules, forming peroxide bridges. The monomer molecules thus obtained subsequently undergo polymerization to form a tough network solid. The whole process is sketched below. Soaps. Substances like soaps and synthetic detergents, which concentrate at the surface of the solution or interfaces, form surface films, reduce surface tension of the solution, and help in removing dirt and dust by emulsifying grease, are called surface active agents or surfactants. The molecule of a surfactant contains two characteristic groups, one of which is water soluble hydrophilic and the other is oil soluble lyophilic or lipophilic. Soaps are sodium or potassium salts of higher fatty acids such as palmitic acid, stearic acid and oleic acid. These soaps are generally obtained by the hydrolysis of oils and fats with aqueous alkalis. The process is called saponification of oils and fats. The fats and oils commonly used for soap manufacture are tallow, tar, lard, olive oil, linseed oil, coconut oil and palm oil. Soaps containing 12 to 18 chain atoms have good cleansing action. Soaps with 12 carbon atoms are comparatively soluble in water, whereas soaps containing 18 to 22 carbon atoms are not useful as soaps because of their insolubility in water. Sodium soaps are generally hard and hence are called hard soaps. These are used for washing off clothes. Potassium salts, on the other hand, are more expensive and produce a softer leather and hence are called soft soaps. They are used for making shaving creams, shampoos, liquid soaps, etc. Transparent soaps are prepared by dissolving ordinary soaps in alcohol and removing the insoluble part by filtration. The evaporation of alcohol leaves behind transparent mass. Soaps are 100% biodegradable, that is, microorganisms present in sewage water can completely oxidize soap into CO2. As a result, it does not create any pollution problems. However, soaps have two disadvantages. Soaps cannot be used in hard water since calcium and magnesium ions present in hard water produce gurdy white precipitates of calcium and magnesium soaps. Soaps cannot be used in acidic solutions since acids present in the solution precipitate the insoluble free fatty acid which adhere to the fabrics and thus block the ability of soaps to remove oil and grease from fabrics. Synthetic reagents. These days, in place of soaps, the substances which are being largely used as cleansing agents are synthetic detergents. As the name suggests, they are obtained from purely synthetic chemicals as compared to soaps which are derived from chemicals which are obtained from natural sources like oils and fats. In fact, synthetic detergents are sodium or potassium salts of long chain alkyl hydrogen sulfates or aryl sulfonic acids. Unlike soaps, magnesium salts of detergents like their sodium or potassium salts are also soluble in water. Hence, synthetic detergents do not form curdy white precipitate with hard water. Further, they can also be used in acidic solutions. However, synthetic detergents have one disadvantage. Unlike soaps, they are not completely biodegradable and hence cause water pollution.